This is an infrared receiver module. It captures infrared signals from devices like remote controls, and it outputs the received data from this output pin. It also has VCC pin and ground pin. So this is a single pin of information kind of device. So we're going to write a driver for this piece of hardware inside the Arduino Uno. So we're going to write software for Uno that understands what command is being issued here, and then it's going to take a simple action according to the information received here. And the information received here comes from a remote controller like this one. So if I press this button or any other button, for each of the buttons here, there's going to be a different pattern of rising and falling edges in the output pin. So this is what this infrared receiver module does. Right now, what we can do is we can open up a data sheet for this particular piece and try to figure out how the particular digital signal is going to be like. But what I like to do is I'm going to hook up a logic analyzer. We're going to use a logic analyzer, and we're going to hook up one of the channels here to the output pin of this device, and we're going to analyze the outputted digital signal when we press the 1 button, 2 button, 3 button, or any other buttons here. And we're going to see, we're going to try to understand how the output forms for each of these button presses. Okay, so let's do that first. So after we do that, we're going to write software for Arduino Uno. We're going to use interrupts, we're going to use timers, and we're going to use low-level libraries. We're not going to use Arduino IDE. We're going to program this in raw C. So we're going to see how to use interrupts and such. All right, I've connected my Arduino Uno's 5-volt pin and the ground pin to the 5-volt and ground pins of the infrared receiver. And also, I've hooked up the output pin of the infrared receiver to the logic analyzer. And I'm connecting both to my computer here. Now, we're going to analyze the single pin format of the output pin of this device. The format that that will come out of the output pin is called a NEC format, NEC. So I'm gonna press some buttons here, then I'm gonna press one of them continuously, and let's see how let's see what kind of a digital signal pattern is going to show up here. All right, let's begin capturing it here. I'm gonna press 1, 2, 3, then I'm gonna press 3 continuously. All right, let's stop it now. Okay, so we've got we've got some signals here. Okay, so the first thing to note here, in my opinion, is that the idle state of the signal. The idle state is high. Whenever there is an event that happens, for example, a button press, we get a falling edge. We get a falling edge signal here. So, apparently, what the NEC format does is it measures the distance between falling edges, like here. If it's very close to 13.62 milliseconds, it decides that this signals a start frame. So after a start frame, there's going to be a stream of bits. The small gaps meaning 1.16 milliseconds, and the larger gaps meaning 2.23 milliseconds. they are going to represent zeros and ones of the packet. So we've got a 32 bits information packet here. All packets consist of 32 bits here. All information packets are 32 bits. And another thing to note here is that the first byte and the second byte are ones complement of each other. So even though the time distance, the time width of the 0 bits and 1 bits are different, the total width of the entire packet is going to be the same no matter what the information is. So we got a 0 here. If we get a 0 here, we're going to need to have a 255 here because they are each other's ones complement. And similarly here we got a 71 and we have a 184. So if you sum them up, you're gonna get 255. So no matter what the information inside this packet is, it's going to have a constant width in terms of time. And let's think about what our decoder software needs to do. So what I'm thinking of is I'm going to connect an interrupt to the output pin. I'm going to connect the output pin to Arduino, and I'm going to configure an interrupt to fire off whenever we have a falling edge sensed in this pin. So I'm going to execute my interrupt service routine right here. I'm going to also execute it right here, whenever I have a falling edge. And then I'm going to measure the time difference between consecutive interrupts to decide if what I just got was a start frame, was a 0 bit, was a 1 bit, or a repeat frame. We also have repeat frames. So they're of length 11.33 approximately. So I'm going to measure the distance between falling edges with help of interrupts firing off each falling edge and the timer inside the Uno board. So that's my strategy, that's my design. We have interrupts and timers. So if we take another look at this, we're going to have, if you count this right, I think we have 34 falling edges for a single neck packet. So we've got 34 falling edges here, 2 for the start frames and 32 for the 32-bit packet. In each of the interrupts that are going to get triggered, it's the same interrupt service routine that is going to be run. So we need to be careful about how we are going to make this interrupt service routine. Because when we are at this stage, we're going to run the same code. And when we are at this stage, we're going to run this exact same code. So we must hold a state inside of our interrupt service routine. So that state is going to change according to the time length between consecutive interrupts. If the time length is 13.62 or close to that, we're going to enter states of decoding incoming zeros or ones. If you decoded 32 zeros or ones, we're going to execute something probably and then go to the idle state. And similarly, if we register a repeat frame, we're going to go inside a repeat state, for example. And then we're going to execute the last command that was registered. That is the meaning of the repeat frame. Repeat frame means redo the last command. So let's take a look at the signal captured from the infrared receiver once more. We've got the start frame, which is like 13.6 milliseconds. We got 0 frames, which are 1.1 milliseconds. We got 1 bits, which are 2.2 milliseconds. And also we got equal amounts of zeros and ones in a packet, because the first and second bytes are complements of each other, and third and fourth bytes are also complements of each other. So in each valid neck command, we are going to have 16 0 bits and 16 1 bits. The consequence of this is each command from the start to finish, they are going to be of equal time lengths. So let's calculate that length. So I've did a little bit of a calculation here. I've added the 13.6 milliseconds, which is the start frame, and 16 times 0 bits length and 1 bits length, which comes about at about like 70 to 75 milliseconds. The importance of this is the timer I'm going to use needs to be able to encode a time difference of at least 70 milliseconds. While doing that, it also needs to be able to give me a granularity less than 1 millisecond, so I can differentiate a zero bit. So let's consider the timer, the 16-bit timer in the Uno board. So it being a 16-bit timer is going to have a counter value of 2 to the power of 16. And the frequency of the CPU that's running inside Uno, it's 16 megahertz. So what is the maximum time value that can be encoded inside the 16-bit timer counter's register? By default, a single tick would be 1 over the frequency. And if we multiply this by 2 to the power of 16, which is the maximum value the timer counter register can hold, then we get 4 milliseconds, which is not enough. So we needed 70 milliseconds or 75 milliseconds. But by default, we have a maximum of 4 milliseconds that can be measured. So we need to slow down our timer, and that is done by pre-scaling the timer. The term for this is pre-scaling. So we've got a pre-scaling factor here. For my design, I've selected the 64, I've pre-scaled my timer 64 times. So in reality, I've slowed down the 16-bit timer from its default value 64 times. So it runs 64 times slower. In this case, a single tick of the timer is going to take 64 times longer. So we're going to be able to encode a time difference of 262 milliseconds, which is enough for our purposes. Like, it's more than 70 milliseconds, it's more than 75 milliseconds. But this was not our only concern. We also had we also need to be able to differentiate between 1 millisecond and 2 milliseconds. So a single tick should take significantly less than 1 millisecond. Well, is it? Well, let's calculate a single tick. So if there were no pre-scaling, then it would have taken this much, but we have 64 times pre-scaling, so it's 64 times slower. And this is the time between a single tick of the timer counter register, which is 4 microseconds. This is more than enough for our purposes. We will be sufficiently be able to differentiate between 1 millisecond and 2 milliseconds. So as a design choice, I pre-scale my 16-bit timer with a factor of 64. So let's see how we are going to do that. All right, in my main C, the first thing I do is initialize the UART module. I'm going to use this for debugging purposes, so we're not going to concern ourselves with this here. The next thing I do is start the timer. All right, what am I doing here? I'm setting some bits inside a register. Okay, and I've got a command here that says initialize 16-bit timer with prescaler 64. Well, what does that mean? Let's take a look at the data sheet. Let me copy this. and go to the datasheet of the MCU and search this register name. Go through a bit. I'm going to land on the timer counter 1 control register B definition, and it's got some bits here and their explanations. If I go back to code, if I go back to my code, I'm setting the CS11 and CS10 bits. So let's go back to the documentation. So the CS11 and CS10 bits, if they are set together, they are going to start the timer with prescaler factor 64. So what is the next thing I do? After the timer, well, I need to be able to sense that I have a falling edge whenever it happens. As a design choice here, you can use different pins. I'm going to use the PD2 pin right here in my Uno board. The PD2 pin is connected to external interrupt 0. So I'm also going to configure that interrupt to fire off whenever there is a falling edge. So let's take a look at the code again and see how I'm doing that. So I've got a function called setup interrupt pin. Let's go inside this. And again, I'm setting some bits in some register. Okay, let's copy this and take a look at the data sheet to see what it means. All right, here's the description. So this is the external interrupt control register A. It's got some bits. Which bits am I setting? Let me take a look at the code again. Well, I'm setting the ISC01 bits. Okay, what does that mean? Well, it means, let's go down a little bit, ISC01, if it's the only bit that is been set, it configures the interrupt 0 pin, the PD2 pin, to only react to falling edges on its input. So this is exactly what I want. This is how I set up my interrupt configuration. So the next thing I need to do is actually enable the interrupt. So what am I doing to enable the interrupt? Well, let's take a look. Again, I'm writing something to a register. I'm like setting some bits inside the register. I'm setting the int 0 bits now in the EI MSK register. Let's see what that means. So in the datasheet, I'm searching the EI mask phrase. All right, what does it mean? The int 0 pin. Well, it's the external interrupt request 0 enabled. All right, which makes sense. If you set this to 1, the interrupt 0 is going to be enabled. But if you actually read this, we also need to set another bit in the status register called the I bit. The I bit is the global interrupt enabled bit. So for any interrupt to occur, this global interrupt flag needs to be set to 1. Well, it's not the interrupt flag, but it's the interrupt enable bit. So we also need to set that too. So let's go back to code. Well, inside my code, I enable my specific interrupt here. Then if I go back to main, also I enable global interrupts with the SEI instruction. Here the standard library provides a function that just inserts the SEI instruction. So we can also go to datasheet again to search for the SEI instruction, but I think it's easier to go to the bottom of the datasheet and show you this. Okay, the SEI, global interrupt enabled instruction. It's going to set the I bit in the status register to 1, so the global interrupts are enabled. Still, I want to show you the status register. So inside status register, there's a bit called global interrupt enabled. If you set that, global interrupts are enabled. If you don't set it, no interrupt can occur. So we need to set it with the SEI instruction. So this was the setup. After this, the main code just goes on with its life with an infinite loop. But then, where's the rest of the code to decode the signal right here? Like, how are we going to decode this? Well, as I said, we're going to use an interrupt in the INT0 pin. So let's go back to the code. A little bit down, we have an interrupt service routine for the INT0 interrupt, which is connected to the PD2 pin right here. So interrupt 0 is connected to this pin. So what I did was this. I've maintained a global state of my decoding stages. So I got the idle state, I got the expecting header state, and I got the decoding state. It's easier to illustrate this on the signal itself. So the idle state, it's when the signal is high and stays high for a long time. Whenever I get the first interrupt right here, the first falling edge, then I transition to expecting header stage because I'm expecting either a start frame after the first interrupt, or I expect a repeat frame after the first interrupt. So I change my state from idle to expecting header state, like right here between these two brown dots. I'm inside expecting header state. And before that, I'm in the idle state. If I'm reading a start frame, then I know that there's going to be 32 more interrupts. And then I need to transition to like decoding the 32 bits, decoding the information kind of state. So I got three states. Let's go back to the code. I got three states: idle, expecting header, and decoding. And I maintain that in a global variable. It's fine. I also maintain a received bit count because I need to like remember which bits that I last read. I also hold the current time because I need to measure it. And I also store the decoded command in this variable, which is like 32 bits because I have 32 bits of data. So let me explain the interrupt service routine. So this is going to be run every time there is a falling edge here. So every brown dot here represents the execution of this interrupt service routine. So what am I doing here? So at each interrupt, I'm going to record the time and reset the timer to 0. So when the next interrupt comes, the value inside my timer is actually going to tell me the time between the last interrupt and the next. So let's go inside this. So this is just setting the current time, the time that I maintain at the global. It just records the timer's counter register, and it actually writes 0 to the timer's register. So we read and like reset the timer, because the next time we are going to read it, if we know that it started from 0 from the previous falling edge. All right, let me show you in the diagram. So at the first interrupt or any interrupt, I'm recording the time value here, and I'm setting the timer to 0. So from this point on, the timer is going to increment, and then I get another interrupt. The same code is going to be run again. Then I'm going to read the timer value in the timer register, and it's going to give me the exact amount of ticks that it took from going from here to here, which is the value I want. So this is why I always at the start of any interrupt, any falling edge, I zero the timer. I'm sorry, I record the timer value, then I zero it. So that's why. Okay, let's continue right here. Okay, so this is what I do at the start of each interrupt. So after this we have a choice. We can be inside of any of the three states. We can be inside the idle state, we can be expecting the header, or we can be simply decoding the 32 bits. So for the demonstration purposes, well, let's start from the idle state, because we're going to be, by default, going to be in the idle state. So the first interrupt comes, and my code runs here, and we're going to check if we are in the idle state. Yes, well, we were in idle state because by default we are in idle state. Then what do? Well, I simply transition to expecting header state. There's nothing to do. So this code is going to be run when we are right here. So at this point, we are in the state of expecting header. The next interrupt will behave differently because the state is different. So this is my design. This is like a simple state machine. So when the next interrupt comes, so I'm going to close this. And I also write something to UART here for debugging purposes. It's not of our concern here. So next time another interrupt comes, we are going to be in the expecting header state. So we're going to go inside this if. If we check this is just a simple check for the state. So what did we do at this stage? Currently we are at this point, right? At this point, right here. We are like measuring the first signal. If it's a start frame, and we need to decide if it's a start frame or a repeat frame. So if it's like 13.6 milliseconds, it's a start frame. If it's 11 point something seconds, has something milliseconds, it's going to be a repeat frame. So we need to decide which inside this code. Okay. So this is very simple. If we got a reset signal, we go back to the idle state because there's like nothing to do. Well, actually, if we get a reset signal, we need to redo the last command. So I need to write some code here in the future. Or we could have gotten a header signal like a start frame signal. Then we need to change our state to decoding state. Very simple for now. We just set the state to the decoding state. Or like if the signal is not either of them, then there's an error. The signal is faulty. It's not a reset signal or a header signal. Then there is some kind of an error. So I go back to the idle state. And at this point, I want to talk about how I measure the time here exactly. A reset signal will be like 11 milliseconds. So in this function, I have the current time because the current time starts from 0 from the last interrupt, and at the current interrupt, it's actually the tick amount from the last interrupt to this interrupt. So this actually is the value that I measured. So the value needs to be between this value and this value. And how do I calculate these? Well, I've got a macro here. So these values should be familiar to you because the reset vector, the reset command takes up like 11 milliseconds. The start frame command takes 13 or so milliseconds. 0 bit takes like 1 millisecond. And at 1 bit takes like 2 milliseconds. Yes. So I got the frequency of my CPU. It's 16 megahertz. I just use it in microseconds, so I divide it by 1 million. Then I multiply it by the actual value that I want to measure, and then I'm going to divide it by the prescaler. So then I'm going to get the ticks, the actual ticks of the time I want to measure. So this is a conversion from milliseconds to ticks, and it's the ticks that I measure, not the actual milliseconds. So I need to like make a translation, and that macro does that. Okay. So if we get a reset signal, then we are done. We just redo the last command, redo what the last command requires. Then we reset. We go to the idle state again. Well, what do we do in this function? Let's take a look at that. Well, we reset the state, we reset the received bit count, and we reset the command. Or like if we had start frame, we go to the decoding state. So we are actually in here now, like at this point. And another interrupt comes right here. And in here it's a 0 bit. So what happens in my code at this stage? Let's take a look. So if the state is decoding, we're going to go inside this if. So if I get a 0 bit signal, and how do I decide if I get a 0 bit signal? Simple. The time I measured is between this threshold of like around 1 millisecond. If it's around 2 milliseconds, then I'm going to get a 1 bit signal. Now, what do I do if I get a 0 bit signal? I decode 0. If I get a 1 bit signal, I decode 1. And by decoding 1, I mean like constructing the 32-bit command, because like think about this, I get the command bit by bit, so I need to like get the bit, shift the actual value for like getting for like preparing the next bit. So when decoding a 0, I just shift the command value 1 bit to the left. That's what I do. And I also increment the receive bit count because I receive a bit. Similarly, if I decode a 1, then I shift left 1 bit and then I increment it because I've decoded a bit, right? And then I also increment the receive bit count. So if we get neither a 0 bit signal or 1 bit signal, then there's an error and we reset. Also, if the last decoding is done, because we are supposed to decode 32 bits, not more, if we have decoded 32 bits, then we are done. The command should be constructed at this point, and depending on the command, I run some code. So that is up to application. And in here, all I'm going to do is write something to UART. I actually write the commands to UART here for debugging purposes. Like I'm not doing anything meaningful, I'm just testing if my code works. After I run the code, then I transition to idle state again to get ready for the next NEC packet. So that's the design. That's the whole design of this interrupt-driven NEC decoder. All right, let's see this thing in action. Well, as I said, the output pin, right, the output pin of the infrared receiver here, the third one right here, the purple one, it's connected to the pin named 2 here. So if I show the schematic for you here, the pin named 2, yeah, right here, corresponds to PD2 pin, which is the interrupt 0 pin. Well, okay. Let me go back here and let's upload this program. First, let's build this program, then upload it. Then we're going to monitor the serial data coming from the USB port. And we are supposed to see decoded data. All right. So I think I've uploaded the program. Yes. Now I'm going to open up the screen application. Now we are supposed to see some decoded data here whenever I press these buttons. Okay. So I press 2, press 3 now. You can see I'm actually printing zeros and individual zeros and ones here. And then in the end, I'm actually printing the command. I'm actually printing the command in hexadecimal format from the UL to A function. Okay. So since it's like shorter than the maximum length, the last byte or last half byte is kind of corrupted. So you can disregard that. Well, so I'm gonna just keep pressing buttons. If you notice, if I press it continuously, it's going to just print out like reset, right? And I'm like printing reset right here. All right, yep. So it seems to be working. Seems to be working like better than I expected. Well, this code has some problems. We're going to talk about that at the next section. So yeah, this is the project. We've actually managed to make a simple decoder which works in a sunny day scenario. We're not handling all of the errors. We're going to talk about them. Well, but yeah, we've used interrupts and the timer to correctly, well, not entirely, like not very robustly, but we have managed to decode this kind of signal with the Arduino board. I hope this was fun. Thanks for watching and see you next time.